Hello. Norman Wildberger believes that the fundamental theorem of algebra has not really been proven. He calls it the fundamental dream of algebra. He has issued a challenge to those of us who are smart enough and brave enough to come to the rescue and finally lay to rest all the controversy surrounding the fundamental theorem of algebra. Well, I think I'm up for the challenge. So without further ado, let's definitively prove the fundamental theorem of algebra. It has been stated that most of the rules, not the theory, of Newtonian calculus work every bit as well and quick as they do when operating within Newtonian calculus. All quaternions are derivatives, and as such must obey the basic rules of Newtonian calculus found in any standard calculus textbook. And to illustrate this fungibility and compatibility of Newtonian calculus with quick, we will now derive the Quickian fundamental theorem of algebra. But before we can do that, we must first establish a few equations and principles. Here we list a few of the elementary rules of Newtonian calculus. You may wonder why the Newtonian power rule is conventionally expressed as f prime of x to the n equals n times x to the n minus 1. And in quick, the power rule is given as x to the n equals nx. Mathematically, both expressions are actually equivalent. To prove this assertion, we first begin with DeMoivre's formula. DeMoivre's formula is given as follows. Now it is given that the cosine theta plus sine theta times the square root of -1 is simply Euler's formula, where the square root of -1 is equivalent to var epsilon, which is the unit quaternion. Therefore, e to the I theta equals cosine theta plus sine theta times the square root of -1, which is equal to the quaternion. Therefore, we may simply rewrite DeMoivre's formula as q to the n equals nq, which is simply the quick power rule. The Newtonian power rule follows the left side of DeMoivre's formula. The UQ turns its operand successively through some angle theta n times, thus generating f prime of q to the n equals n times q to the n minus 1. In the quaternion power rule, the UQ, or unit quaternion, turns its operand through a single angle of n theta once, thus producing q to the n equals nq. Both operations produce equivalent results. Therefore, since unit fractions are derivatives, then any such unit fraction must be a quaternion that obeys the quaternion rule I equals jk. Therefore, the Comedian system of unit fraction calculus asserts that I equals jk is equivalent to j plus k is equal to 1 over q, which is equal to 1 over q plus 1 plus 1 over q times the quantity q plus 1, where I, j, k, and q are all integers. And since the unit fraction is a quaternion, then its reciprocal must be a quaternion. And since the reciprocal of any unit fraction is an integer, then all integers must be quaternions. We now prove that all integers are derivatives. The immediate corollary of this proof is that all integers are quaternions. Therefore, quaternion equals beta over alpha, which is equal to a rate, equals the derivative, equals n, equals any integer. We now prove that any and all numbers are quaternions. You will find that there are some Quickian equations that will prove to be of great utility. One such equation is q to the n equals nq, and another is plus or minus I equals plus or minus 1/2. The quaternion I holds a special place in both quaternion algebra and in Quick. The prime mover of quaternion algebra is I, or more properly, var epsilon, the general term for the UQ or unit quaternion. We will now show that I, being a unit fraction, is not coincidental, but plays a major role in the algebra of both the quaternion and Quick. We now present the Quickian proof of the law of quadratic reciprocity. As a corollary to this proof, we may just as easily generate the plus or minus conjugates of 1, which are plus or minus I. Therefore, 1 to the 2n plus 1 equals negative I, and 1 to the 4n plus 1 equals I. Therefore, P and Q are quaternions, then the law of reciprocity proves that quaternions obey the law of indices. That is, quaternions behave and act as exponents, and therefore may be considered as being exponents. Now that we have laid the necessary groundwork, I now present my margin proofs of the Fundamental Theorem of Algebra. Here we present our first proof of the Fundamental Theorem of Algebra. Here we present our second proof of the Fundamental Theorem of Algebra. The key to proving the Fundamental Theorem of Algebra is recognizing that since any polynomial root is a y-value of 0, then it must also be a limit of 0, which makes all addends on the right side of the equation derivatives, which must all sum to 0. It is clear from both proofs that the Fundamental Theorem of Algebra is simply a Newtonian expression of DeMoivre's formula, which brings us back full circle to Euler's formula. Note that plus or minus 1 is equivalent to plus or minus 1/2, which is equivalent to plus or minus 0. The two states of plus or minus 0 is not an algebraic artifact. Not only do the two states of plus or minus 0 exist, but they must exist, especially if we are to accept the dual existence of E and E star. This is exemplified by the dual existence of P of x is equivalent to 0, and A times x to the n is equivalent to negative 0.